you are looking to get started with cloud native geospatial, then this is the tutorial for you. In this tutorial, we'll be taking a deep dive into Source Cooperative, which is a data portal that works pretty much exclusively with cloud native geospatial data and cloud storage. It allows you to interact with data living on S3 buckets without actually having to host the data yourselves and bring that into any of the different tools that accept cloud native geospatial formats. So throughout this tutorial, we'll be taking a look at how to use Source Cooperative, get signed up, pull data into a variety of different tools from QGIS, GeoPandas, DuckDB, PostGIS, and Apache Sedona and Wherobots. We'll be working with very large data sets and show you exactly how you can use this and gain some skills with these new file types as well as cloud tools. So let's go ahead and dive in. So first, let's start with Source Cooperative. If you're not familiar with that, it's basically like a data sharing utility, right? And that's what it says here on Radiant Earth, which sponsors the initiative. So you can see here that allows you trusted organizations and individuals to share using standard HTTP methods. So what that effectively means is it allows you to share data and communicate it over the web, is basically what that sums up. Now, when you come to Source Cooperative, you'll see this page. You get basically the same sort of listing here that tells you exactly what it is. It's not data that you have to purchase or have a subscription. And most importantly, you don't have to manage infrastructure. That's really important here, is that you don't actually have to manage anything yourselves. Shares it with HTTP methods rather than using APIs. So you don't have to communicate over an API, make multiple API calls to data. It just allows you to work with it over the web. Now, overall, the service is fairly simple. There's some different data sets you'll see here that are either featured. You can take a look at all the data you can get access to. There's different data from raster data, vector data, all these different things. And then down here, you can actually see some different information you can take a look at. You can filter into the specific repositories of data. So this gives you kind of like a full listing of everything that's there. You can click into the different data sets and go from there. But what I usually like to do is kind of search here by file type or a specific type of tag that you can see here. So in this case, we can click on GeoParquet, and that'll filter to all the data sets that provide GeoParquet data, which is vector data. In the same sort of theme, you can also look at raster data. This could be COG. You can also filter by the raster tag as well to see what that data looks like. Now, I'd also recommend taking a look at some of the information here that gives you some information about the project, but it's pretty straightforward. It's just this repository of data. If you want to, there's a Slack channel that you can join to get involved and effectively learn more about the project. Now, there's two things you need to do. First of all, you need to sign up to actually use this or make full use of this, I should say. So you want to sign up here and get signed in. I'm going to go ahead and sign in with my account now. So once you're signed in, you'll see there's a few basic settings here, just some information about who you are and then the ability to change your password. So it's fairly straightforward. There's not a lot of complexity here or anything like that. To get started, let's take a look at some of the different data that's here. So the data that I've been using most recently is this Eurocrops data set, which is cropland around Europe. So to get started, let's take a look at this data set. You'll see there's lots of different types of data here from this Eurocrops provider, but this here is the main repository looking at this data. Now, when you actually click into a listing, you'll see here that it's a data set combining all publicly self-described crop reporting datasets from countries in the European Union, and it pulls it into all cloud native geospatial formats, mostly the vector formats here, which is really nice. So you'll get some information here. There are some modifications to the data. You can pull it in and see that there's, a translated name, a machine readable name, things like that about the crop itself, and use some different ways to access the data and pull that in. You can pull in this with PM tiles. It recommends visualizing with a felt map. And I think there's actually a map here that you can actually open up and take a look at this data. So here's the data that we're looking at. And if we zoom all the way in, we can actually see some of the individual cropland. So if we get down to a detail here, you can actually see, okay, here's the grassland. This is green silo maize. This is pasture meadow, so on and so forth. So you get a sense of how much data is actually in here and how much you can actually use. So it's quite detailed and has quite a lot of coverage. So first things first, let's go ahead and take a look at some of the data that's available. You're going to access this tab here that says Browse first thing. Now you can see here that there's a few different files. There's just a README dataset, which is effectively what we just read. And we can also take a look at some of the files. We have GeoParquet projected, unprojected data. We have the PM tiles, which is the tile specification. And here's a nice little preview of what we can actually see. So very similar to that. No styling or anything, just the pure tiles on a map here. And if we zoom all the way in, you can see here's the individual croplands. So like I said, very detailed data and stuff like that, but effectively you can serve these as web tiles just using that, which is great. There's also a file database, or sorry, flat geobuf, and the full Parquet file. Now, when you click into the GeoParquet projected, which is the data we'll be using, you'll see here that there's basically a few different types of data from different country codes. Here we have France and Netherlands and things like that. So you can get individual countries in different files, which is nice. And then you can actually see when this was pulled in from. So these are all from the Eurocrops 21. And then I believe this is the year it was created, but this is the full data set that's pulled in. Now, if you want to, without signing in, anybody can see this data. I can go here and actually pull this in. You can just download this, and this will start the download of that GeoParquet file. So it's actually quite easy to just download a file like that, and you can pull that in. That's the first step to actually getting this data, is you can just pull that file in and upload that and load it into a map. So actually not too difficult to do that. Now, as it relates to QGIS, I promised that would be a part of this demo. And if you are a user on Linux or Windows, it definitely can be. You can just simply load that data in, drag and drop it, or add it as a vector file like you would any other file type. Very easy to do, no extra work needed. But I am unfortunately on a Mac, and for some reason, the Macs are left out of that and have extra things to install. So going over to geoparquet.org, I can see here that Windows and Linux ship directly with GeoParquet support, and Mac can do this, but you have to install Conda, which I don't install because I have too many conflicting versions of Python on my machine, and I don't want to add another. And then you just have the config, add in the channels, and then add in the drivers for that, for QGIS and libg.airparquet. And then QGIS will open in the terminal. So there's like these extra command line steps that you actually have to do that. But there's another way we can kind of show effectively how this works, and we'll quickly show you how to build that using felt and creating a quick felt map. So I'm going to create a quick map here. I have that file that I downloaded. And the nice thing about felt is you can just basically drag and drop this here, and it's going to upload that file to the map. Pretty simple, straightforward. I don't have to do any translations or anything. It's basically going to help me load that in. Now, as that loads up, you can also actually do the same thing with those PM tiles data sets. So if I go here and go to Browse, I have that PM tiles endpoint here. I can go ahead and copy that, and that would allow me to upload those as tiles as well. So as that uploads here, I can also add another layer that allows me to do that from URL, which is basically the same process here. So you can see it looks good, add it to the map, and go ahead and add those layers. And those are hosted on the web, so that's going to be very fast to load up, faster than the file a little bit. And you can actually pull those in here and see that it's almost all the way loaded up, and then I should start to see that data on the map, which you can see here. So if we zoom in here, and you can see the actual files and everything like that, and I can start to style my map and do some things there. So as that loads up, you'll see the Parquet file loading up as well. It's probably loading slow because my upload speed on my internet has not been good lately. So we'll let that load up and then show you what the result looks like. So as you can see here, all the data loaded up. This data set comes from Slovakia. And now we have all of the fields in Slovakian. You can see this gets pretty granular here. If we pop into the satellite, we can see here are all the fields that are overlaid and growing things. It's quite a detailed data set as we see that. And of course, we can style this if we want to make it a little bit more interesting. We can base it on the categories and pull it in, I believe, by the translated name. Actually, that is the localized name. So we have to pull in the English name here, which is translated here. And then you can see the different categories. So here we have, if we pull all the way down, this is renter. I don't know exactly what that is, but this looks like sweet corn and things like that. So you can see all of the different things that are grown here. So winter wheat, stuff like that. So like I said, very detailed data that you can actually take a look at and see. So that's kind of your first step is you can get these files individually, you can download them. Like you said, you just click to download, nothing too crazy there. But what's more interesting is being able to use it over the web and actually use it as, sort of a connected endpoint. So that's what we'll take a look at now. So what you can see here is that you can select what's known as a data mirror, right? And this allows you to mirror this data on S3. This happens to be in the US West region. And then you can actually generate temporary credentials to do that. So what I can do here is you can see I'll get my credentials and I'll see that the URI is here. I can get access to this endpoint, which changes slightly from the other endpoint. So it's, it's a different endpoint here, Source Cooperative, so on and so forth. Here's the region, access key ID, secret access key, and session token. You need all of these to effectively use that data directly from S3, which will be a little bit faster to use. So that's a nice piece that you have there. And then here's how you can do some quick usage examples, and we can actually test this out to see how we can connect to that. So I'm just going to open a terminal window here. Now you do have to have the AWS command line package installed. So as long as you have that, you should be good to go. But basically this passes in all of those keys, and now it'll basically store those different keys in there so I don't have to write them again for that different command. And this will effectively allow you to, first of all, just look at what's in there. So if I open this up, I'll explain what's happening in this command here. So you see I'm using the AWS command here. I'm calling S3, which is the service. That's the simple storage service, 3 S's, or S3 as it were, is which they call that, which is what's known as their blob storage, which you can store anything in cloud storage. It could be image or logs or text or videos. It doesn't matter. PDFs, you could store anything. So it's just blob because it's anything you want, and it's effectively organized in files. So in this case, it's organized under C. Holmes or Chris Holmes, and then the Eurocrops dataset. And this ls command is just going to list all the things in there. So if I go ahead and run that, it's going to list back all the files. And you can see here, it's the folders here. These are actual folders, GeoParquet projected and unprojected. So if we run that command again, and I write GeoParquet projected, and go like that, that's going to list all the files in there, which you can see it's the same things that we have before. So basically all those files that we saw previously. So that's effectively what's happening here is we're just listing those files out. And if you want, you can download through this directly. You can transfer these to another bucket. These are all options that you can do, but effectively allows you to read that data directly from AWS, which is what you're doing here. So this is cloud storage. It's as if you were using cloud storage yourself. It's using it natively just through the same APIs, but just allowing you a temporary credential to get access to that. And that's important to point out here is that this credential is valid for only a specific period of time. So it's the same day. It looks like it expires in about 5 hours or something like that. So that's when it'll actually turn off and you won't be able to use that anymore. So you get a temporary credential that will turn off at some point. So that's effectively what's taking place there. Okay, so now that we've at least shown our data and how we can pull it into at least Felt to start with, and I do promise you, you can pull it into QGIS if you are working on Windows or Linux, or if you do those extra workarounds on Mac. But to show it actually in QGIS, we have to do one extra step, at least for my machine, which is to pull that data into PostGIS. So that's exactly what we're going to do here. So just to show you what this looks like, you effectively have to pass this in. I'm going to use GDAL to do this. You could, of course, download the data and load it in if you want to do that. But the whole idea is you want to leave that data effectively on the S3 server. So what we need to do is we need to pass in those same credentials. And what you're going to do is just pass it in as these, what we call exports. So you're going to pass in these same arguments. They should look relatively the same as before. You have your AWS default region, access key, secret access key, or sorry, access key ID, secret access key, session token, and then this one extra thing that we didn't have before, which is this no sign request, which is basically, it doesn't require you to like pass those things in, or it's effectively like a anonymous call to pull that data. So it's for most public data, that's a argument you want to include. So you're going to effectively export those, and we can see that we have these once we've run that in. So I can go ahead and run that in my command line and then validate that down here to see that. Here we go. Yes, those are, all saved effectively. And then this is just a quick command to make sure that you have access to that Parquet format, which we do. We can see, yes, there is Parquet, GeoParquet, all those different things in there. So then we're just going to run the ogre to ogre command, OGR to OGR, whatever you want to call it. That's going to pull it into my PostGIS instance. And if you don't have a PostGIS instance set up, check out this tutorial because I've done this before, and this is the exact same steps, exact same configuration, so it'll be all the same things. But you'll notice one key difference, and that's right here, is that this would normally look like this. It'd be S3://. Now, we don't have that because it's this kind of like virtual URL system, and that's part of GDAL where you can actually read hosted URLs using this other command. So we can take a look at that over here. So these are these like virtual file system commands for GDAL. So there's a few different ones. There's ones for zips. There's ones for, as you can see over here, things like .7z archives, tars, gzip files, all these different things. And then ones for network-based file systems. So you have different streaming types and things like that. But there's one for S3. If we search S3 here, you can see that there's this network-based one across these different types. So this, I believe, is Google Cloud Storage. You have S3 here. There's probably a few different other types here that you have, Microsoft Azure Blob Storage, so on and so forth, right? So you have different types of storage here that you can actually access as well. So all of those allow you to access those cloud file systems, but directly without pulling the data in. So there's no like, nothing's really happening apart from the data is reading in from that system into wherever you want to put it to. This command can be modified if you wanted to do that a little bit differently, or maybe turn it into a different file type. You can certainly do that as well. But for us, we're just going to pull it in there. So I already pulled this in once. I'm just going to add the exact file name here, but just add the _new since I already did that once, just demonstrate it. If you don't have GDAL installed, or you can't, you could also use Docker to do this. This is a little bit of what that configuration would look like. I've covered this exact process in my spatial SQL book. So this is pretty much the only way I use to import data to PostGIS, be it on my local machine, cloud service, anything like that. It's super straightforward, easy to use, pretty quick, and does the trick. So I'm just going to go ahead and run that here. And what's going to happen is right now it's just reading from that S3 bucket and then pulling that in to my PostGIS database locally on my computer. So it is transferring storage, but you could imagine this going to another PostGIS in a cloud or something like that. Same type of thing is going to happen. It's the same sort of like transfer service that's taking place there. So I did get this one warning of polygon type and multi-polygons. So there was one little error there, but for the most part, it works just fine. And then that completes, so I know that that runs. And let's take a look in QGIS to see how that looks. So if we look here, you can see I have my file. That's all here, and you can go ahead and add that to the table, and there we go. That's the same thing we saw before. Let's add a little base map here so we can see what we're looking at. And let's just do one specific area, and there we go. There's our farm fields. So works just fine. Same process, just into PostGIS. So taking that file, once again, you're not really transferring storage until, depending on where you land in PostGIS, but there you go. It's very easy to do from there. Okay, so in the next part of the tutorial, we're actually going to take a look at how we can use cooperative with GeoPandas. So if you haven't installed GeoPandas, you can use this notebook. In fact, all the code you're seeing here will be in the link in the description, so you can check that out and actually take those and use these notebooks just as you were seeing here and follow along in the video. So with that, if you need to install anything, you can take a look here. You can install GeoPandas. And then this is just a toolkit to actually pull in S3 data and then just matplotlib to quickly show that we actually have data and prove that out. That's all we're doing there. So if you need to, you can install those libraries. That command will take care of that for you, and you can just run this in the notebook. Now, you can run this on Google Collaboratory. You can run it in Jupyter Lab. I'm just using a Python virtual environment and VS Code here. So I'm just running my notebooks that way. So to get started, I'm just going to import GeoPandas, and I'm going to basically build this dictionary of my storage options. So same things as before. You have your key, I have my secret and my token here. So I have everything that I need ready to roll there and just pulling that in. So we'll just store those. So I'm going to go ahead and read this file. It looks just like any command for read Parquet. So you can just see I'm passing in that S3 URL here. And then just that single file for Slovakia, I think it's like 78 megabytes. So it's pretty small overall. And then as you can see here, I have these storage options, which is passing those things in. And we'll just read like any normal file. So I'll go ahead and pass that. It takes 14-ish seconds, I found, at least on my computer, to read that entire file in. And as you can see here, what's going to pop out is that plot of all of the data. So we have all of the fields in Slovakia, which is on a map here, and we can see here that it in fact pulled that in, which is great. That's exactly what we want to do. So the next thing I actually want to do is take a look at some partitioned data. Now, if you're not familiar with partitioning, it's a common practice in a lot of different databases or kind of data structures, if you think of it that way. Be that in PostGIS, and Postgres has a notion of partitioning. A lot of the big data warehouses, BigQuery, Snowflake, Redshift have partitioning, and any Spark-based environment has partitioning as well. And a partition is basically a splitting up of the data. That's kind of the easiest way to think about it. You can split that based off of many different things. You could do that based off of a categorical element of the data. You could do that off of a date as another common element, maybe the year or the month that the observation is in. Or you could do it off of some category or thing in the data. And we'll actually see here what that looks like in the Overture map schema. But it allows you to split that up, and within some of the big data processing frameworks, that allows you to kind of filter your query or your what you're looking for based off of that partition. Now, partitioning, there's a lot of different things to kind of know about it and stuff like that. If you're interested in this, I actually have a course on geospatial data engineering. It's in the Spatial Lab, which is my online community. If you want to check that out, there are some information on that in the comments. But what we're actually going to do is take a look at this data, which is the hosted on Source Cooperative. It's the fused partition from Fused.io. They're doing a geospatial partition on the data for Overture maps. And you can look at that listing here. This has the most up-to-date data as of this recording, which was on September 18th, 2024. And what you can see here is that it's split up into the themes. So you have your themes like administrative boundaries or land use and things like that. And if you actually go into the data, we'll take a look at it here. So here's the most recent version of the data. You can look at maybe things like buildings or divisions. We'll look at divisions in this example, and we'll go to division area. And then you see all of these basically smaller Parquet files here. And these are the geospatial partitions, which is what you can do to kind of partition. If you have a notion of like a spatial index, that's kind of another way to think about it, but it's partitioning it on geospatial data. So you see these files are all in more manageable sizes and formats. So what that looks like here is that you can see here we have this folder structure where theme equals divisions. That's a partition. It's known as a Hive partitioning from the Hadoop or Spark ecosystem, I believe is where that came from. But we're just going to use the same sort of format here and pull that in. And then let's just take a look at what the data is. I meant to put that below. So we'll just go like this. So let's just inspect the data quickly. We can see here, here is our data. We have some information where it's coming from OpenStreetMap, things like that. We can see here where these locations are. And what we can also do is we can quickly take a look at the map here and just see where this is. So you can see this is what the data is pulling. And I actually have no idea where this area is because I have no base map or reference here, but you can see that this is a subset of the data. We're pulling in that one partition specifically. Here we go, specifically within this area. So I have no idea where this is. I think it looked like it was in the United States. I'm not 100% positive, but it's a geospatial partition. So that 111 file is one specific area. So imagine we want to pull in something or some subset of that data. Now, if this is a kind of a tricky thing, if you were reading the documentation for read Parquet in GeoPandas, let's go take a look at that. So you see here, you have your path, column, storage options, which we've already covered, and a bounding box, right? Which is what you can do here. And then you have this whole thing, these KW-args, right? Which is basically these inherited arguments of this function. So if you go here, you see that's coming from PyArrow Parquet read table. And in here, you can actually see, oh, I have this notion of partitioning. I can use that partition, which basically means you can read that whole folder and it'll read everything in that folder structure. And you have this notion of filters, which allows you to filter within that query. So the best way to think about that is you can see here is that we have this partitioning passed in. We are telling it's a file partition. So I'm not reading a specific file here, as you can see that. I'm just reading into this folder. So I've already filtered out a ton of data. I'm only looking at the theme of divisions and the division areas. So I'm cutting out a lot of the stuff in Overture Maps already just by filtering down the file system. So it's not actually querying the entire data set. It's all, oh, I just need to look in this folder and just look at that data, which is one big advantage. And then what I'm doing here is I'm creating a very small bounding box around a specific area. And within the data in Overture Maps, if we go up here and take a look at that data that we pulled in, you can see here that it has this bounding box stored in here. So if I pulled that in and went to that specific bounding box column, you can see I have an xmin and xmax, which defines the bounding box around each individual polygon. So I can actually filter that with this, and I'm going to create that. So you see here that what I'm basically doing is pulling in this argument for data set, and then field. And then within that field, there's the bounding box. And then within the bounding box, since it's a dictionary, I need to get the xmin. So if you can see here, I'm going basically into the bounding box field and just grabbing that one for xmin and saying if it's, greater than or equal to 5.959, so on and so forth. So I'm grabbing a specific area in the globe here, and then I just want the subtype of neighborhood. So I combine that filter just by basically doing a Python join with the ampersand that combines it into one single thing and pass it into filters. So it's a pretty clean way to do that, but I have to use this pi arrow dataset sort of argument here and pull that in. And what this is going to do is it's going to look in that folder. It's going to say, this is a partition folder, so I know to read those partitions and then just filter the data there. So I can just read across that entire data set and see exactly where I want to pull that in. And then we should start to get that data in for just the neighborhood subset of that data in there. So this is the nice thing about these files with cloud native files. Once again, all the storage is handled elsewhere, but I can actually filter this pretty efficiently just by passing in the right parameters that I need and just getting that little bit of data back that I actually care about in this specific area. So once that pulls in, you'll see here, this is ultimately the data frame that we pulled in. I'll be honest, I forgot which area I pulled this in, so I think I have to go back and take a look and see where exactly in the world I pulled this in. But this is the neighborhoods data. Let's see if we can actually figure that out here by taking a look at this. And here we go. So I believe this is in France. That's right. Okay, so France is where I pulled that in. So that's how you can use this data with GeoPandas, right? It's remote data. You're not storing this. It's living somewhere else. And you can do all this nice filtering, especially with the GeoParquet data, which is really, really nice. So you can actually pull that in and makes life a lot easier. Okay, so next we're going to take a look at how to use source cooperative data within DuckDB. Now, DuckDB is going to be fairly simple. What's great about DuckDB is that, number one, it's an in-memory database, which means that you can use it basically anywhere, which is really nice. If you want to use it in Python, which is what we'll use today, you can use it locally on your machine. You can embed it in some other workflow. It's really powerful that you can embed it in different places, and it has the ability to read these external files, specifically GeoParquet, which is just supported as of version 1.1, and read data from cloud buckets like S3, which is exactly what Source Cooperative is. So it makes it a logical choice to show how you can actually read and do some analytics on that data. So I'm actually installing two libraries here. The first is DuckDB, and I'm specifically installing it at version 1.1.1. I said the GeoParquet support came with version 1.1, which is true, but there were some fixes in 1.1.1 that made it a little bit easier to do some exporting and things like that. So if you're watching this in the future, this probably won't be an issue, but just if you want to be aware and you're watching this when it's published, that's something you're going to want to take care of. The other is the IBIS framework, which is sort of like a library that allows you to have a single data frame for multiple different backend technologies. So that works with lots of different tools, like it could be, Apache Spark, it could be DuckDB, it could be, a database like Postgres, BigQuery, lots of different things. So it gives you that common framework. And what I'm doing is I'm installing the specific flavor of the IBIS framework, which is for geospatial and geospatial and DuckDB. So if you haven't installed these libraries, you can do that. And we'll take a look at how you can use IBIS with DuckDB here. So just make sure you have imported your libraries and then run that check that you have version 1.1.1 or above. Now, to set up IBIS, it's pretty simple. You have these options. I'm going to set that to true. And then the configuration for the interactive, which is the max number of rows for 100. If you want to see more rows or things like that, you can do that. And then you just set up this connection to DuckDB, which is just establishing to an in-memory database. And that's all that that's doing there. Now, this should look familiar at this point. We have a key, a secret, and a token, which makes total sense. And what we're going to do is against that connection, so that connection value here, we're going to run a few things. We're going to install the spatial library that comes with DuckDB, so you don't have to do anything extra. It just comes along with that. But you do have to call it to actually get it, to run, and then load that library. And again, so load spatial. And then all we're going to do here is create this secret, as it were. So this is secret stores the information about our connection to S3. And there's lots of different types, but you have the type of S3. And then we're just passing these variables in, the key to the key up here, secret, and the session token. The last one is actually setting the region. So you can see here, this is US West 2. And if you noticed in the S3 URL down here, that also is US West 2. So we're just setting that up as well and establishing that. So we can run that. We'll have our token stored for this period of the session, and we can always call back to that. So what's a little bit different about IBIS is that you're going to create a connection to that specific file, and then it will execute queries in a more Pythonic data frame way, but still getting the power and the backing of DuckDB, which is nice. So what I'm doing here is establishing connection to this that same file we've been using, and just connecting that. So that connection is set up here, and I can just establish that connection, and then it works just like any other data frame. So if I wanted the first 5 rows, I can use the .head function, which will give me the top 5 rows of that data frame, and it's going to and basically execute that query for me, but not with SQL, which I think is interesting. I obviously have a preference towards spatial SQL, so I have an easier time writing that. But if you are kind of coming from the data frame world, this might be a little bit easier. The other thing I really like is the ability to just kind of see, it's a little cleaner of a view. So I can see the different data types are styled by different colors. I can get some information here on the data types. There's a few other pieces I like about it, and as you're doing some data exploration and things like that. So that's what I like about the IBIS framework. It's just a little common or cleaner like that. But of course, you can just write this as you would anything else with just normal SQL. So what I'm doing here is I'm going to select star from, selecting all the columns from, and call the read parquet function. So what I'm going to do is call all of the files in there and create one giant file, but I'm just going to return the first 5 rows, right? So I can actually call that and see, okay, here's the first 5 rows across everything, but it's just using that wildcard. So since I'm calling this, I'm just going to call everything that ends in parquet. The star represents a wildcard, which if there's any match there, and the thing ends in .parquet, it will get called in. So we can also do is just get like see how many. So we'll just call the count to see how many rows there are, and you can see here that it's quite quick to actually count over every single file. And there's about 22.8 million, almost 22.8 million individual kind of records in this data set, which is nice. I mean, it's just very quick to do this in memory. So DuckDB is pretty straightforward, right? It's fairly easy to run queries like this, access the data, store the credentials that you need. And you can combine that with the IBIS framework should you want a little bit more of a Pythonic API to do that. So that's it for DuckDB. It's pretty straightforward, but yeah, definitely very easy to use with GeoParquet within Source Cooperative. Okay, so now that we have pulled this data in through all the different tools, we'll go to our final sort of processing tool, which is in Wherobots and Sedona. So if you're not familiar, Wherobots is a cloud platform that allows you to run Apache Sedona on environments within Wherobots. So if you're not familiar with Apache Sedona, we can take a quick look at that. So Apache Sedona is a cluster computing system for processing large spatial data, right? What that means is that it provides distributed computing, which means instead of just processing on one single server or node, as it were, it spreads that operation out over multiple clusters of compute. So imagine instead of you just running it on your one computer, it would run it on 4 computers. And that's a little bit of a simplistic version, but more or less that's what it is. And it can run on multiple tools to do that. Apache Spark is the most common, but you could run Apache Flink or even on top of Snowflake, which are all distributed computing systems. It allows you to write operations in Python or SQL, so it allows you to do that. I mean, it's completely open source, so that allows you to do all of these different things and integrate data from lots of different sources. Now, what Wherobots is it's a cloud platform that allows you to do basically 3 things on top of Apache Sedona. So normally you could pull a Sedona down. If you did on your local computer, you could still run things, but you wouldn't have access to the distributed computing. You'd have to connect that to some computing environment, be it Spark, be it a cloud hosted service on premises, wherever that might be. You have to connect to some sort of distributed processing to do that. Now, Wherobots provides that for you. It's also it's custom built, right? It's its own spatial computing. I think it's likely the only spatial computing environment that's built, or any computing environment built specifically for geospatial. So that's the advantage there. It has the notebook services. It allows you access to basically what's called Wherobots DB, which is a database, but it's connected into a file system. So if you're familiar with Apache Iceberg, that allows you to build a data lake and add a database functionality for inserts, updates, deletes, things like that on top of just files. So that's what the Wherobots DB brings. And then there's some other AI features, which we won't have time to get into today, but we're just going to look at data processing within Wherobots. So when you log in, if you want to create an account, you can basically open this up and create an environment. There should be multiple environment types. If you're on the community edition, you'll get access to this tiny environment, which is the sort of the out of the box one. And then there's other versions available as you use it and grow up from there. So that's what we'll do, and you'll just click this open notebook, and then you'll load into this notebook environment. This is the notebook that I've built to accomplish this. So I'll just walk through what I did since I processed everything already. And the first thing is you build this Spark context. So you have your configuration, and then you build your Sedona context here, which is basically connecting the notebook down to the Spark instance. More or less, that's what that's doing. Now, Wherobots provides you access to a AWS S3 bucket, so I can just import OS and then get access to that user bucket here, which is important because one thing that I found while doing this was that Source Cooperative uses like a custom URL endpoint that is not like one of the normal S3 endpoints. Normally it's like s3.amazonaws.com or something like that. Because it's not that, I have to manually download the files from Source Cooperative and then load them into this storage system. So I've talked to them about that and let them know that there's some specifics that don't let me do that today, but that should be changing. But overall, it's actually quite quick. S3 is very easy at transferring data. So all I'm doing here is I just set up a source, which is our Source Cooperative data, and my destination, which is temporary keys for my Wherobots bucket. So then I download the data here, and I give it the source bucket and prefix, destination bucket and prefix, download every file, and then load it in. So as you can see here, it goes through, copies, and then loads it into the source where it needs to go. So from there, you are going to pick that GeoParquet folder, and I'm going to create what's known as a Spark data frame. So this is same terminology as a GeoPandas data frame, but it's doing it in Spark or Sedona in this case. So it's really a Sedona data frame because Sedona provides the spatial capabilities. So here's my folder location, and you can see I'm just using the folder. All the files in there would be under there. So each individual file name would be there. And what I'm doing is I'm saying create the data frame from GeoParquet, which is the files we've been using. Here's the folder location, and give me everything here and merge it into one giant data frame. Right, and you can see here's all the schema of the data we're working with, which is basically what we've seen this whole time as we go through. And we have our geometry, of course, which is what we want. And you can see here in total, this is about 22 million, almost 23 million individual polygons that we're working with when you read the entire data frame. Now, to do a really large scale spatial operation, what I chose to do is to see the distance to the nearest river. And what's nice is that we can actually, see all of the rivers from the Overture Maps data. So if you're not familiar with Overture Maps, that's a foundation that brings together these really large scale spatial data sets, things like Google Open Buildings or OpenStreetMap and things like that, and centrally brings them into one. So you can see here we have the Overture Maps data set. This is the most recent version here, and here's the older versions as well. And then it breaks it into some of the different topics and things like that. And so you can see these are actual tables that are loaded into that data lake structure. But basically they're files, right? They're files here, and you can see the schema and all the different things, but this is already up there for you to have access to and easy to use and access. So the first thing I'm going to do is just basically create a data frame of just the data I need for this operation, right? Within a distributed computing environment, you want to just select, and this is actually goes for basically everything that you want to do, but if you're processing less data, it's going to be more efficient. So what you want to do is basically just filter down to the data that you need. So I'm just going to grab my geometry, some IDs, and then this is the field type, which is the actual, what's growing there. And this is the English translated name. So I do that through SQL. As you can see here, it's just standard SQL select, and then from the data frame. So I'm using that data frame as the table, basically, which is what you can do, which is the nice piece from Spark. So now that I have all of that ready, I'm just going to create a temporary view within the context of the notebook. So field, then create or replace temporary view. And you can see here's my schema, which is exactly as we defined in the SQL up here. Now I'm gonna do the same for the rivers here. So I'm gonna select this from this specific version. The previous most recent version was in July. And so I'm gonna use that version from the water, and I'm just gonna select rivers here. And this selects everything from that. So you can see here it has all the data that is in that Overture Map schema, which has the ID, geometry, the bounding box features. It has the sources, where it's coming from, the subtype, the names of that, what's the primary name, the common name, any other information about that, level, so on and so forth. Wikidata is saltwater because this is the water version, so things like that. And you can see here that this is about a million or 2.2 million rivers globally that we're looking at. So I'm going to create that view here. Once again, rivers, create or replace temporary view. And then this is where you had some of those different kind of Spark pieces or, distributed computing processes that I'm still in the middle of learning myself. But so this is what I'll try to explain this as best I can here, but we're basically doing what we call a broadcast. Now in distributed processing, you're basically splitting the data. So let's imagine we're processing these 22 million rows of data. Instead of doing that in one pass through, we're actually taking that and splitting it into these multiple nodes, doing that over in multiple locations, and then bringing it back together at the end. Now, what the broadcast does is to say if we're doing a large scale spatial join or something like that, where we have a small data set, we're going to broadcast that to every node so it has access to that completely. So we can actually send that out to all of those individual nodes so it has access to that, so it doesn't have to call back or do anything otherwise to grab that. So it makes the join more efficient because every node has access to that smaller data set, or in this case, the rivers. So I then create that view again. So it's a temporary view that I'm broadcasted out. And then this is just a repartition, which is just splitting the data up for those fields to send that out over the multiple nodes. So there are some kind of manual or semi-manual steps here to control how the join is going to go. And that partition splits the data up to send it over the multiple nodes that are going to be built up. And that's basically, there's from what I understand, there's a rule of thumb. It's about 2 to 3 times the number of cores that you're working with. So that's the very back of the napkin math that you're doing there. And then once again, you create that view. So I have access to that. You're basically caching that. And then you perform the SQL join or nearest neighbor join here, right? And that's what you want to be able to do. Now, what's the advantage of having the control over these different things when you're broadcasting those out and doing the partitions manually is that you kind of control how the data is going to be processed. Generally, also, that's going to be a little bit more cost effective than letting the computer handle it. It's just going to do it in the way that it seems best. It might be fast, it might not, but it's going to try to figure it out for you, and you have less control, which means they might just charge you more, especially in the cloud computing. So what you're basically getting is if you are paying for something like this, you have the control. It's basically you get access to the environment. You have to do a little extra work to make those things efficient. It's not much when you really look at it. There's really a few steps with something like this, and then go from there. So really what you're looking at here is the k nearest neighbor join. I'm gonna get the field, the type of the field, the river primary name. So the nearest river, the primary name of that. I have an ID here. for that, that Inspire ID, which is, I think, a European ID. And then I'm going to get the distance, the spherical distance. So ST distance sphere. So spherical between those two. I could get a raw distance just on flat, as the crow flies, but I'm going to use the true spherical distance. And then that's between the field geometry and the river's geometry. And I'm going to give that an alias of distance. And then I'm going to actually pass in the geometry of the field as well. So since we're doing the join, we're going to do the fields part and the join here. And then we use this specific function, which is STKNN. It's actually AKNN, which is a little bit of a faster join. And we can take a look at the documentation there just to see what that looks like. So this is basically a join operation to find the K nearest neighbors in a pointer region. And you can see here that the function is similar to this, but uses some approximations within that. So it's a little bit faster. There's some filter push down considerations and things like that. But you can see the function type here is we have our right table, the nearest table, the K neighbors, or how many neighbors you want to find. So in that case, we're finding one. And then using the spheroid is true or false. You can choose to do it either way. So the spheroid will increase the operation time, more or less, if you want to use a spheroid nearest neighbor distance, because it's not calculating straight line distance, it's calculating over the sphere of the globe, which makes sense. So we have our field geometry, we're calculating it to the river's geometry. We want to find one nearest neighbor, and then we're not using the spheroid false. So this will store that SQL. This won't actually run it, so it doesn't execute anything here. We're going to join that, create the temporary view of the join here, and we can see what the schema will look like out. And then here's where we actually do the processing bit. So we're actually doing when I actually timed this out. You can see the start and the end time. And to do that join took 844 seconds, not minutes. So I was like, wait, which one? So I think that's like 13, 14 minutes, something like that, which is quite fast overall, very, very quick in terms of processing. And if you tried this on anything else, that you wouldn't be able to get to this close of processing time, be it a data warehouse or at this scale, it's quite efficient. So that's what's really nice, is you can do this at pretty high velocity and volume, especially given the amount of data. Now, the tricky part, or not the tricky part, I think what's actually even more interesting is that we're doing this from a polygon to a polygon, right? And polygons are made up of multiple points. It has to take all those vertices into account and figure out the distance from the nearest vertex to the other vertex. If we were doing this from a centroid or points, it would get even much, much, much faster. So there's even more things you could potentially do to make that more efficient. But overall, it's quite fast. And that's what's really been impressive about this type of technology to me. So we've even though we're like pulling this data in, that's what we're allowed to, we're pulling there. And I can actually spit this out as a GeoParquet file. So I wrote this to GeoParquet within that S3 bucket. So it's spit that out. It does some of the partitioning pieces for me, which is also really nice. So I can have some of those partitions. And then I actually created this as a layer here. So I created that as a table so I can reuse it if I need to within my Wherobots DB. So overall, that's pretty much it. It's kind of some basic Python, some basic SQL. You have to know some of these distributed computing things, and I think I'll keep learning more about that as I go along. But it's really not, when you boil it down to it, it kind of makes sense when you think about it, when you're envisioning what those distributed systems look like. It's not too terribly complex. So here's what this looks like, right? Here's the data. I loaded up just a chunk of this data here, and you can see the lighter colors are basically where they are closer to a river. So you can kind of get a sense of where there are rivers flowing through here and here. And the darker areas mean they're further from a river. So this is just a small area in France. You can kind of see where there's likely a river going through here. There's likely a river going through here. And then we can actually see what those rivers look like. So if we zoom in here, you kind of have to guess where the actual river might be, but we'll try to find one of these areas here. I think there's a river somewhere in here. So we can just try and guess. So bear with me as I go through the map here. And you can see here, so here is the land. This is, fallow cropland, it looks like. This is winter wheat. And then it says, here's the nearest river. And I'm not even going to attempt to say that, even though I took French in high school. La Faison, maybe. I'll try. If anyone's from France, you can correct me. And you can see here, it's 153 meters from that, or in distance here. You can see here, here's the distance to the river. And then here's the river itself, or here's where that river is. You can see here it gets the sense of how close it is to that river. And that's basically it. You get this kind of cool visualization, but there's obviously some practical of implications to this as well. You want to be able to understand how, from a perspective, how close you are to a river or an area or water body, and do that at scale. These sort of large scale spatial joins, that's something you could do as well. But of course, as you start to scale up these operations, you need to be considering, okay, what type of operation am I doing? What type of compute infrastructure might I need to do that? But like I said, that's kind of the next scale here. So give you a sense of like how you can start on the small scale and go all the way up to these very massive spatial operations, which is what I wanted to do all through the scope of Source Cooperative. So that's basically it for the tutorial. We went through QGIS, PostGIS, we went through loading that data with GDAL, loading it with GeoPandas, loading it with DuckDB, and then finally all the way into Sedona and Wherobots to show that at scale. So I hope to do more videos like this showing how you can use cloud native data and data stores. What's nice is that through all these operations, you're effectively just using the data that lives somewhere else, and you can pull that into your operations, scale that up as you need to do more and more complicated things with this data. But I hope you can kind of see that there's some efficiency here for especially larger data sets and things like that. And I hope you can find this applicable and actually use some of the data on Source Cooperative, or if you're feeling ambitious, contribute some data to Source Cooperative as well. So yeah, I hope you enjoyed this tutorial. If you have any questions, let me know. I have posted the notebooks and information down below in the description. So if you want to actually do any of this yourselves, you're more than welcome to, and follow along. And like I said, and the easy part is you don't have to download any data. It's all on Source Cooperative. So thanks for watching. I hope you enjoyed this. Any questions, drop in the comments. I'll make sure to do my best to answer those as we go along, and see you next time.